Okay, so in this video, I'm going to discuss chapter 7. All right, just so you know, chapter 7 is broken down into two parts. I break it down to two parts, right? We will have the first part, we'll talk about simple harmonic motion, and then the second part, we'll talk about progressive waves. So this video is going to focus on the first part, which is simple harmonic motion, right? So first things first, how do we know some motion or at least a body is undergoing simple harmonic motion? Well, we look at its acceleration, and then we look at its displacement. They should be directly proportional to each other, but they should have opposite direction, right? So if I have A going to the right, then I will also have Y going to the left. Okay. So that's how we know it's a simple harmonic motion. Now, how do we find an equation for that? This is just a relationship. So how do we find? We can assume a solution, and the solution needs to be, so simple harmonic motion simply means that it is periodic. So in other words, we want it to go up and come back down, go up and come back down. And I don't know about you, but that looks like a sine wave to me. Okay. So I'm going to assume some solution. Okay, I'm going to assume a sinusoidal solution. So I'm going to have yt equals to y max sine omega t. Why do I have omega and why do I have t? T because this motion of going front and then coming back is as a function of time, right? And then omega because we have some frequency to it. So we have some period, and then if you have some period, you have some frequency. Okay, so and then this would relate back to our omega. So if I were to have simple harmonic motion based on this solution, I can take its first derivative, dt, and I'll have omega y max sine omega t. This is the first derivative. Should be cosine. Okay. This is the first derivative. And then the second derivative, which is equal to a, its acceleration, is going to be negative omega square y max sine omega t. Now, if you've noticed, these two looks exactly the same. So I can simply just replace it. And say that my acceleration is equal to negative omega square y t. Okay. Now, of course, this would also mean that my acceleration is a function of time. Okay. So again, what is this omega? This is simply the angular velocity squared. Okay. Now, one of the key feature for this function, so let's just draw it out. One of the key feature of this function is that we have y max. We will have y as a function of t. Then we have t over here. Y max is basically just the maximum displacement here. And we have a special name for it. Our special name for it is that this is what we call amplitude. Okay. Now again, we have our function yt equals to y max sine omega t. Okay, we have this equation. Now I want to inform of you, or I want to clarify to you that this generally will have dimensions of length, right? And its SI unit therefore will be in meters. Whereas this part, the trigonometric function, should be unitless. Okay, Omega, however, of course, will be in radians per second. T will be in seconds. Sorry, in seconds. But that also means is that my y max, my maximum displacement, will also have dimensions of length and SI unit of meters. These two must match, and these two must match. You can use radians per minute, but you will need to convert your time into minutes as well. You can do that. Or you can use cm as the amplitude, centimeters, but your displacement will also have to be in centimeters. So please be very, very careful with when you're doing questions. Okay? So now we already have a function for displacement. What we want to do now is to look at velocities. So we want to look at velocities for this object that undergoes simple harmonic motion. Velocity, right? And there's two main functions that you need to know. The first one is when you're given a time. So in other words, the question might sound like, determine the velocity when time equals to 2 seconds. That kind of question where they inform you the time, you need to have a function of vt, v as a function of time, velocity as a function of time. This is fairly straightforward. I can take the first derivative of y, right? And this is simply y max sine omega t. And we've seen this before. This is simply going to be y max cos omega t. Sorry, y max omega cos omega t. So we have a nice function there. But of course, it's useful to just, rather than having to write 4 letters, let's just write one letter. I'll write down y max equals to amplitude. Therefore, I have Vt is equals to A omega cos omega t. So that's the first velocity equation that we need. The second velocity equation that we need is going to be when they ask you determine the velocity when the object is, for example, 2 meters from the equilibrium. Okay, so we need a velocity equation as a function of displacement. Now, how do I find that? Well, I know my solution yt is simply going to be a sine omega t. This is the first thing that I know. The second thing that I know is my vt is simply going to be omega a cos omega t, right? Now, these two, we have a trigonometric function that relates between them, and it is going to be sine square theta plus cos square theta equals to 1. Okay, so if I can just take the squares, so y over a, take the square, plus cos square, so v over omega a, take the square, that would equal to 1. Now, of course, I want my v to be the focus, so I can just rearrange this. So I'll have v over omega a squared equals to 1 minus y square over a square. Of course, I can rearrange this to have v equals to omega a, then the square root of 1 minus y square over a square. I can further simplify this by simply multiplying into the square root. I have v equals to omega, then the square root of a square minus y square. Now, it's very important for us to remember from mathematics that whenever we take a square root, we should remember to include a plus plus positive negative sign. So we'll have that. Okay, so my function, so my equation for velocity as a function of displacement will simply be two values, right? Omega square root of a square minus y square. Okay, we need to write the summary here. For velocities, we have two equations, right? We have v as a function of time. You have omega a cosine cos omega t, and then we have v as a function of x, which is equals to plus and minus omega and square root of a square minus y square. If I have t, I need to look for t. If I have y, which is displacement, I need to look for y. Okay? So we've looked at displacement functions, and we've looked at, sorry, this displacement function. Let me just remind you that we had y as a function of time equals to a sine omega t. Then we had v t equals to omega a cos omega t. Then we also have vx equals to plus and minus omega square root of a square minus y square. Okay. What we can do with this is to talk about energies. Okay. Two main energies I want to talk about, which is going to be potential energy and the kinetic energy of the object. And of course, once we do that, we do the potential energy and the kinetic energy, we can just add them up so that we can have a total energy. Okay, so let's do kinetic energy first because it's easier. In general, you have K equals to half mv square, right? So if I wanted as a function of time, I can simply substitute the function for v, this one. So then I'll have half m omega a cos omega t. Then this whole thing should be squared. Then I'll have k as a function of t, half m omega square a square cos square omega t. So that's as simple as it gets. Just substitute it in and then square it. Okay. What else do I need to do? Well, I can also find my kinetic energy equation as a function of displacement. And that would require me to substitute instead omega, then the square root of a square minus y square. I need to square that. I'm left with half m omega square. Then I have a square minus y square. The square root goes away. So then I can have two equations for kinetic energy. One as a function of time, and then one as a function of displacement. Okay, so now we've discussed about kinetic energy. Now that we've discussed about kinetic energy, what we want to look at now would be the potential energy. Okay, the potential energy. To make our lives a bit easier, what we can do is we can consider Newton's second law. Okay, we can consider Newton's second law, and we can consider F equals to ma for simple harmonic motion. So SHM, we can have we can have A equaling to negative omega squared y. So I'm left with F equals to m and then negative omega squared y, right? So that means I have negative m omega square y. And then what we can do at this point is expand on y. Expand on y. But before that, we have to compare it with Hooke's law. So Hooke's law tells us it is f equals to negative ky. Yep, okay. Now, if I compare between them, I have y here and I have y here. The negative cancels out. I'm left with k equals to m omega square. Okay. M omega square. So then, I can consider for a string, its potential energy is actually equal to half ky square. I can substitute this into that. So I'm left with m omega square, then y square. Again, remember your y is simply your a sine omega t squared, that is. And then I'm left with half m omega square a sine square omega t. So this is my equation for potential as a function of time. It's quite simple to see my potential energy as a function of displacement is simply going to be half m omega square y square. Okay. Now, if I were to talk about total energy, which is simply the summation of kinetic energy and the potential energy, I can use any of the equation, either as a function of time or as a function of y or displacement. But let me just use as a function of y, right? So what I'm going to do is I'm going to add k as a function of y plus u as a function of y. So u as a function of y. If we look back on our equation for kinetic energy here, we can copy that down. I have half m omega square a square minus y square. That, and then plus our equation for potential energy here. I'll have half m omega square y square. I can take out the half m omega square, and then I have a square minus y square plus y square, so they both cancel out, and I'm left with, so e total half m omega square a square. So as you can see, the total energy is independent of my position. Okay, that's a very important point. Independent of position. Okay, so that means that my kinetic energy is always constant, which brings me to the next part, which is going to be, we will learn how to graph certain things out. Okay, so at this point, what we're going to do is we're going to graph things out. Okay, there's a few things. The first part is that we're going to graph as a function of t. Okay, let me just remind you that my yt is equal to my a sine omega t. So that's a sine function. That's perfectly fine. And then I want to remind you also that my velocity as a function of time is going to be omega a cos omega t. So it's going to start from the peak. right? And then of course, last but not least, my acceleration, function of t, is simply going to be negative omega square a sine omega t. So I'm going to start from 0 as well, but I'm going to be in the opposite direction. Okay. So again, this is going to be my function of yt. The green one is my function for at. And then last but not least, the red one will be for velocity. Okay, this is the first graph that we want to draw. The second graph that we want to draw is going to be for energies as a function of displacement, which brings me again back to this part, which is the total energy is independent of position, so it's just going to be a straight line. This is going to be a straight line. Oh, that's not a straight line, is it? It's just going to be a straight line. Okay, and then I have my potential energy and kinetic energy. My kinetic energy is going to be at its highest when y is equals to 0. So my kinetic energy maximum K max when y equals to 0. So when y equals to 0, it's going to be max. So I'm going to have something that looks like that, because there's a square there. It's quadratic. And then my potential energy is going to be max. So U max when Y max. So in other words, if I were to just draw a straight line here, then my potential energy is going to look like that. So this is going to be my U, this is going to be my K, and this is going to be my total energy. Okay. Okay, so what I want to do now is going to look at cases. Two main cases I want to look at. The first one being the first one being a spring system, and the second one will be a simple pendulum. Okay. And in both cases, what we want to know how do we calculate its period. Okay, so by the end of the derivation or explanation, we want, okay, so the period is equal to blah blah blah. Okay, so let's look at the spring system. Let's look at spring system first. It can be horizontal or it can be vertical, but either way you have to have a spring. And when you have a spring, you can apply Hooke's law, F equals to negative kx. I can also apply something that is moving, so I can apply Newton's law, ma. Okay, here I want to change my x into y because it's just a displacement, it's the same thing. And then I can take these two equations and equate them. I will have ma equals to negative ky. I can rearrange that. I'll have a equals to negative k over m y, and then I can compare that to our simple harmonic equation just now. So negative omega square y. I have y on the right side, and I have a on the left side, and I have omega square equals to k over m. I can take square root on both sides. What I'm left with is omega equals to the square root of k over m. We're not looking for omega, we are looking for period. And period is equal to, or at least omega is equal to 2 pi f, which is just 2 pi over t, right? So then what I'm left with is 2 pi over t equals to the square root of k over m. I can just reshuffle that. I will have t equal to t over 2 pi equal to the square root of m over k. And I'm left with t equals to 2 pi times square root of m over k. All right? So this is my period equation for the spring system. Spring system. All right? Now it's a bit more difficult, but let us do that. The next part we want to do is for a simple pendulum. Okay, for a simple pendulum. There's a diagram that I will have to draw, but let's assume that we have a pendulum. So here's the ceiling, here's my pendulum. Okay, I have a string of length L. Okay, and then I have the string being pulled such that it makes some angle. So this angle is theta. I have weight moving down, right? Okay. And then I have some displacement. So this pendulum is going to travel in a circular path like that. And this circular path is going to be S, arc length of S. And then I have pulling the pendulum is just a component of the weight. So that component is simply going to be sine theta. So this W, let's call it Wx. Okay. So then now I want to ask, what is pulling the pendulum? What is giving force? What force is acting onto the pendulum? And I'm going to equate it to MA. Okay. So the force that is pulling on the making the pendulum move is simply going to be negative W sine theta, or negative Wx, right? So it would be negative Wx, right? Which is equal to MA. Negative Wx is just negative mg sine theta, which is equal to MA. That's nice. I can cancel them out right now. I have negative g sine theta equals to A. Now, if theta is very, 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 very small, then my sine theta is going to be approximately theta. Okay, kind of counterintuitive, but that also means that my theta is approximately my S over L. Okay. So now what I can do is I can substitute it. Okay, I can have negative G S over L equals to A. If I rearrange that, I will have A equal to negative G over L times S. S is just displacement. So then I can compare it to negative A equals to negative omega square Y. S and Y is the same thing. So then I'll have omega square equals to G over L. Again, rearranging this, I can have omega equals to the square root of G over L. And this would lead us to period being equal to 2 pi square root of L over G. Okay, so to summarize this part, the last part, the case study, for simple pendulum, my period is dependent on two things. It depends on the gravity. It depends on the gravity, the local gravity, and it depends on the length, Doesn't depend on anything else. For spring system, my period depends on, let me just, there we go. My spring system depends on the mass of the object and the spring constant of the spring. Okay, so that is all for the first part, which is simple harmonic motion.